So let's talk about another confidence interval. This time we talk about the confidence interval for the standard deviation or variance. So in this section, we will still focus on the point estimate and the confidence interval. So the best point estimate for the sigma square is just the S square. So S square is the sample variance. It's just the best point estimate for the population variance. Sigma square, of course, the best point estimate for the sigma is just the S. So we will talk about the confidence interval. Not like the previous two confidence interval. The previous two confidence interval we have already covered is just the confidence interval for the proportion and the confidence interval for the mean. These two confidence interval follow the same format. Remember, point estimate plus minus margin of error. For the proportion, the point estimate is the p hat, right? Sample proportion plus minus margin of error. For the confidence interval of mu, mean value, we use x bar, sample mean plus minus margin of error. But this one, for the sigma square or sigma, we do not follow that format. We will have a new format. And we will talk about a new distribution called the chi-square distribution, which means we will have a new table. You can also find your chi-square table in the content of your blackboard if you do not have your chi-square table in your book. Okay, so this is just the formula of the chi-square distribution. You don't have to memorize that formula actually. Let's just show you the formula of chi-square distribution. And when we check the chi-square table, we need to check two critical values. Remember, when we check the z table or the t table, we only need to check one critical value. No matter z table, t table, we only need to check one critical value. But for the chi-square table, we need to check two critical values. Why we only need to check one critical value for the z table and the t table? That's because no matter t distribution or the z distribution, they are bell-shaped curve, right? If they are bell-shaped curve, they are symmetrical. So we only need to pick one side, one critical value. Then plus minus, when we get to the margin of error, we plus minus to get to the two-sided limit. But for this chi-square table, it's not symmetric. It's not symmetric. So we should get two-sided critical values. So first off, or for chi-square table, we need to check two critical values. But how we check the two critical values? Let's see. And another one is we also need to check the degrees of freedom, just like when we check the t table. Z table, we do not check the degrees of freedom, but for t table, we need the degrees of freedom. Here, chi-square table, we also need the degrees of freedom, but it's just the same degrees of freedom, n minus 1, okay? It's still n minus 1. This is the shape of chi-squared distribution, so we find it's not symmetric, right? And it's not bell-shaped curve, it's skewed to the right side. That's the reason why we need to check two critical values. And that's the reason why the confidence interval for variance or standard deviation does not follow the previous format, plus minus margin of error. So the values can in your chi-square table, so by the definition, by the meaning, cannot be negative. By the name, chi-square, so it's square value, cannot be negative. It's possible to be 0 or positive, never negative. So for your t value, for your z value, it's possible to get to the positive value and the negative value. But for the chi-square table, always positive or 0, right? Never negative. And this curve shows you different degrees of freedom. The shapes are different for the chi-square table. And if the number of degrees freedom increases, if it goes infinity, then the chi-square distribution, if it's the degrees of freedom, or let's say the n goes infinity, increase, the chi-square distribution approaches a normal distribution. So you will see degrees of freedom 20, this one more flat, right? More flat and more close to a normal distribution. If it's degrees of freedom equals 1000, then it's very close to a normal distribution. So if you have your textbook with you, the table A4 is the chi-square table. We will say here, this is not correct one. Does not follow this format. This is the wrong one. This is the wrong format. This format is just for the confidence interval for the proportion and the mu, but not for the standard deviation or variance. It's not the correct one. It's not correct one. Okay, make sure don't use that format. And we will say the chi-square table is just corresponding to the area in the top row. So we can get to the area just like the t-table in the top row. T-table, remember, we have top row. The very top row shows you the area in one tail. And in your chi-square table, we also have the area on the top row. And each area is cumulative area to the right. This time it's the cumulative area to the right. Remember our Z table, it's just the cumulative area to the left. But for the chi-square table, it's just the cumulative area to the right. So let's check an example to help you understand how to find the critical value in chi-square table. So in this example, we know the 22 IQ scores. So from here, we will know n is equal to 22. So we total have 22 IQ scores. 22 is the sample size. But we want to construct the confidence interval for population standard deviation. So that's the sigma, population standard deviation sigma. Okay, and we know we need to find the two critical values. If we are talking about chi-square table, we need to find both sides critical value. So how can we find the left side critical value and the right side the critical value? So let's check what's the definition of these two critical value. Left side means the critical value of chi-square separated in area of 0.025 in the left tail. Why this one is 0.025? Remember, this one is still the half alpha value. It's still the half alpha value because the confidence level here is 95%, which means alpha value is 1 minus 95%. It's 5%. If alpha is 5%, then the half alpha is 0.025. That's why we got 0.025 here. Similarly, another critical value, right tail critical value, separates the area of 0.025 in the right tail. let's check the graph to help you understand. So this one, chi-square left tail, right? So this is the left tail has 0.025, half alpha. And another side, right side critical value, right tail 0.025. Add them up, half alpha, half alpha. And we also need the degrees of freedom to check the table. So if the sample size is 22, of course, the degrees of freedom is 21, n minus 1. So let's check the right side critical value first. If you have your chi-square table with you, let's check the top row. Because we already know the chi-square table gives you the area cumulative to the right side. So we already have the right side cumulative area, 0.025 for the right side critical value. So this part, 0.025. We can automatically check the value 0.025 in your top row. Top row, find 0.025. Check that column. Find the corresponding degrees of freedom. So remember, degrees of freedom is not n. It should be n minus 1. So it's 21. And we check the table. We find it's 35.479. Okay, so first we check the right side critical value. We can directly use the half alpha value. So half alpha value here is 0.025. We check 0.025 in the top row. Okay, top row 0.025 half alpha to find the right side critical value. Of course, we need degrees of freedom 21. We can find the first critical value. The right side critical value is 35.479. And the second step, we will talk about another critical value. This time, left side critical value, a little bit complicated than the right side critical value, because we cannot directly use 0.025. 0.025 is for the right side critical value, right? Right side. But this time, we only have the area cumulative to the left of this critical value is 0.025. But remember, we can only find the area cumulative to the right in your chi-square table. So if the area cumulative to the left of this critical value is 2.025, we need to get the area cumulative to the right side, right? So that's why we need to use 1 minus half alpha this time. If we want to find the critical value of left side, we only know this small part on the left is 0.025. But if we want to check the table, we need to get the whole part, right? The bigger part, the cumulative area to the right side. Of course, this whole part is 1 minus 0.025. So it will be 0.975, and we're going to use this 0.975 as the area to find the critical value of the left side. So remember, if we want to find the left side a little bit complicated than the right side, do not directly use the half alpha value. Half alpha value is just for the left side. If we want to get to the right, half alpha value is just for the right side, it's just for the right side critical value. If we're going to find the left side critical value, we should use the value 1 minus half alpha. So in this case, it's 0.975. Then we go to the chi-square table to check 0.975 on the top row. Then we find 0.975 is just the third column. And we also need to use the degrees of freedom 21. We can locate the critical value here is 10.283. So again, we start with the right side. because that one is a little bit easier than the left side, right? We directly use the half alpha value, check the top row. Then use the degrees freedom to locate what's the right side. Then we move on to the left side, because left side we use 1 minus half alpha. Then check the degrees freedom to locate the left side the critical value. So again, for the chi-square table, you need to check both two sides critical values, not the single one. Not like the C table, T table, you only need to check one. Chi-square table, again, two critical values. So this is the most important part for the confidence interval about the variance or standard deviation. After we know how to find the critical value, now we could construct the confidence interval for variance or standard deviation. Let's check the notation together. So is sigma always the population standard deviation? Sigma squared is the population variance. Of course, S squared are from sample standard deviation, sample variance, and is again the sample size. Here we still have the margin of error E. But we do not use the previous format. The most important part is we have two critical values in our chi-square table, in our chi-square distribution. So, of course, each time when we try to construct the confidence interval, we need to check the requirements, right? No matter the confidence interval for proportion or for the mean or for the variance for the standard deviation. So we quickly go through this part. The sample should be the simple random sample. It's always should be the simple random sample. And the population must, here, this one said must have normally distributed value. This one, when we do the confidence interval in the mu, this also have this one. The population is normally distributed or the sample size is greater than 30. Remember that requirement for the confidence interval for the mu. This time we have more stricter requirement here. Must normally distributed. If it's not normally distributed, can cause large errors. But when you do your exam or the quiz, you do not have to check the requirements because I've already checked the requirements for you. But the problem is when you do the confidence interval estimating in your later work or in your real life the problem, maybe you need to check the requirements. So in your test, it's not necessary. And after we check the requirement, we check the format of the confidence interval for the variance. Let's see here. This is the formula. This is the correct format for the confidence interval of variance. So it's not the point estimate, not like this one. Proportion, point estimate p hat plus minus margin of error. For mu, x bar plus minus margin of error. But for the variance, you check here, it's not the same format. Remember, we have to find two critical values. And you will find that the right critical values goes to the left, and the left critical value will be the denominator of the right side. So that's for the variance. And of course, we know the relationship between variance and the standard deviation. If we are talking about the standard deviation, sigma, then we need to have the square root for both sides. take the square root for both sides. The remaining part is just the same. The right side critical value will be the denominator for the lower limit, and the left side will goes right be the denominator of the upper limit. Let's check the round-off rule. It's still one more decimal places than the original data. It's just the one more decimal places than the original data. So the procedure for construct the confidence interval for sigma or sigma square. So first, always check the requirement. And the second step, we need to use the degrees of freedom, right, in -1 to find again two critical values. After that, we just write our confidence interval into that format. Make sure you know sometimes we are talking about a confidence interval for variance, so that will be sigma square. Sometimes we're talking about the confidence interval for standard deviation, then that will be sigma. If it's sigma, then you will have the square root in your formula for both sides. Okay, so if it's just the sigma, take the square root. And we always keep one more decimal place than the original data. That's the round-off rule. So confidence interval can be compared variation in different data set. In the different data set, just compare the variation. Okay, just compare the variation. It's not like mean, not like proportion. Compare some value. They actually compare the variation. Let's check. Example to tell you how to construct the confidence interval. So it's the same example, IQ score. We still have 22 scores. So sample size is 22. Of course, we have a standard deviation, right? We have the standard deviation, that's the S. Okay, standard deviation is S. Of course, this is sample standard deviation, so we use S. And we try to construct the confidence interval, 95% confidence interval, to estimate the sigma. So if we're talking about sigma, standard deviation, so don't forget you should have a square root in your formula for both sides. So most important part, we should find the correct critical values, right? Of course, the first step is just try to check the requirements. So we will say if we draw the histogram, we will say this shape close to the bell shape, we will say it follow normal distribution. Now, second step, we need to find what's the critical value. Remember, we should use degrees of freedom n minus 1. So if n is 20 to n minus 1, degrees of freedom will be 21. And we start with the right side critical value. So we start with the right side critical value. We can directly use the half alpha value to find the right side critical value. Again, in this case, half alpha is 0.025. 0.025. So we directly use this 0.025 to check the chi-square table top row. Check the top row, okay? Then we can use the degrees of freedom to locate what's the right side critical value. For the left side critical value, we use 1 minus half alpha. 1 minus half alpha in this case is not a 0.975. So we check the top row to find which column is 0.975. Then use the degrees of freedom to locate the left side critical value. So the most important part when we can try to construct the confidence interval for sigma or sigma square is the critical values, two critical values. So after we have two critical values, so this is the chi-square right side, this is chi-square left side. then we only need to plug into the formula. We know n minus 1, right? That's the 21. We also know the s, so we can find what's the s squared. And because here we are focused on the standard deviation. So don't forget, after we get the confidence interval for variance, we should take the square root for both sides. This is the final answer we are interested in, because we are interested in the confidence interval for standard deviation, not variance. So if you get the confidence interval for variance, don't just stop there, because this problem is talking about the standard deviation. So again, it cannot be expressed as this one. It's not the correct form, okay? Only P and mu follow that format, but for sigma or sigma squared do not follow that format. Okay, we will also need to know how to find the minimum sample size when we try to construct the confidence interval for variance. So we use this format. We use this formula. We use this formula. So no matter what table we're going to use to find the critical value when we construct the confidence interval, when we talk about the sample size, you realize we only have one critical value. That is the z. So remember, when we talk about the sample size for the proportion estimating, we talk about z. We use z as our critical value. In the confidence interval of mu, most of the time we're gonna pick t-table to check the critical value when we do the confidence interval estimating. But when we check the sample size, we still use the z as our critical value. So here, when we talk about the confidence interval for the sigma square or sigma, we will use the chi-square table to check the critical values when we try to construct the confidence interval. So that chi-square critical value is just for the confidence interval, just like t, still for the confidence interval. If we talk about the sample size, we always use z, okay? Just one critical value, it's just z. But it's complicated to use that formula. So maybe we can just check the table to find the sample size. So you can use the table to find the corresponding sample size. So for example, if we want to construct the confidence interval, 95% confidence interval, and we know the D, so it's within 1% or 5%, we will find the corresponding sample size. So this D means the maximum error. So of course we can use you always use the formula, but the formula maybe sometimes is not easy to get the confidence interval. Let's check this one. So this time we want to determine the sample size, and we know the 99%, and we know our estimate is within 5% of the true value of sigma, which means the maximum error here is 5%, right? So we could use the table 99 confidence interval, so we check the bottom part, and the maximum error here is 5%, so we will find the minimum sample size we need is 1336. Okay, so it's about the sample size. It's about the sample size. So basically, we just check the table to find the sample size for the sigma square or sigma. Okay, so that's all for the chapter 7. Okay, again, in chapter 7, the first two confidence interval follow point estimate plus minus margin of error. But the last one, sigma square sigma, does not follow that format. We should check two critical values when we talk about sigma square or sigma. And the format of the confidence interval is totally different. So that's the most important part.